we finally come to what I think is the most important unit in the whole course. This is going to pop up everywhere, no matter what we do. Quantum mechanics, source of energy, thermodynamics, you name it, this is going to keep popping up over and over and over again. So being familiar with these notions is key if you want to do well in this course. So I encourage you to pay very close attention to this lesson, and then we're going to spend probably 2 weeks just working on problems, because this has to be so well ingrained in your brain that it's worth spending the time for you to master this. Now, even though you've done this last year, we didn't do this in a very refined way, so we're going to spend the time to work on these concepts a lot more and to really elicit what energy really is, where it's stored, and so on. But the key here is really work. From the concept of work, all the other quantities emerge. So last year I told you that if I had a certain body here and I did a certain force on the body and it moved a certain distance d, I told you that work was the force times the distance. That's what I told you. And the justifications that I gave you for this was that work is a measure of really how much work, like physical work, we do, right? So if I move a box 10 meters, I've done some work, but if I move it 30 meters, I've done a lot more work. So it makes sense that the work that I've done is proportional to the distance that I move things. And also, if I've been moving a 300 kilo box, I've of course done much more work than if I moved a 10 gram box. So of course it makes sense that the more force we need to do to move something, the more work we did. So this is the, let's just say, intuitive justification for why works this way. Why work works this way, that just sounds good. Anyway, let's just move on. Now, before we go on, I'm just going to tell you that this formula doesn't really work. And there's a reason that it doesn't really work. So for example, what if I'm trying to move this thing this way, and it does move, let's say 20 meters, but the force that I'm doing is this way. Now, did it move because of the force that I'm doing? Well, obviously not, because I'm not even doing the force in the direction that I should be doing. If I do the force this way, they should move this way. But if it moves this way, it didn't move because I moved it. So we can see that if I apply a force in a direction that's perpendicular to the motion, then I'm really doing no work at all. So, but according to this formula, I'm doing exactly the same work than if I was doing the force in this way. Similarly, I can do the force this way, and it looks like I'm doing exactly the same amount of work, but of course I'm not, because here a good amount of my force is lost in this direction. So the only force that I'm interested in is really the force in the direction of the motion, not just any force that I do. So how can we put this into a formula? Well, how do we take this force and say, no, we only want the component that's in the direction of the motion? Well, again, what am I going to say? We use trigonometry, exactly. I'm sure you said trigonometry in your head. So if this is an angle theta, and I'm doing a force, and I'm only interested in the component of the force that's horizontal, what do I need to multiply this force by? Stop the video and tell me in your head. Yes, correct. We need to multiply this by the cosine of the angle. So this is the actual definition of work. Work is force times distance times the cosine of the angle between the force that I'm doing and the displacement that I'm trying to achieve. And this is a formula that does work and does tell us the right answer, for example, when this is perpendicular, because when this is perpendicular, cosine of 90 is 0 and the work is 0. So this works wonders. Now, before we move on and start exploring the consequences of this, the first thing that I want you to tell me is what the units of work are. And I hope you remember this from the IGCSE. If you don't, I will refresh your memory. Now, remember, this means units of work equals units of force times units of distance. And what are the units of cosine? Pause the video and tell me. Okay, well, hopefully you realize that cosine has no units, and therefore that's it, force times distance. And those are Newton meters. But of course, we don't call Newton meters, we call them joules. And we call them joules because there was a guy who made huge leaps in the study of energy, and his name was Joule. He actually had a beer factory, a brewery, so people didn't take him very seriously. But actually he was, quite smart. Okay, now you'll see that I've changed the formula a little bit, because instead of distance I wrote displacement. And the reason that I wrote displacement is that this is a lot more rigorous than writing distance. So that's why I put the S here. Most of the times D will work as well, but I'm just going to use displacement to be a little bit more serious about this. Now, the next question that I want to ask you is, for example, imagine that I'm holding a piece of string. So this is my arm, and I know, yeah, my hand is horribly deformed. And here's a piece of string, and what I'm doing is I'm swinging this like that, so, making it follow a circular motion. And the question that I have for you is, if this is the tension, how much work does the tension do on this stone that I have attached to it? Pause the video and tell me. Now, you probably gave me some kind of figure or formula or something like that, but because you didn't realize that the tension and the displacement, now the displacement here is in this direction. And now what I need to do is take a look at the angle between the displacement and the tension. And you can see that for a circular motion, this is a right angle. Now, what does that mean? Well, what this means is that work will be equal to the tension times the displacement times the cosine of 90, and that's 0. So the work that this thing is doing on the stone that's moving circularly is exactly 0 joules. So you need to be very, very careful with this. Every time that you're calculating work, you need to take a look at which angle there is between the force and the displacement. I've told you that we can get work if we multiply the force times the displacement times the cosine of the angle. However, imagine that I have a spring that's in its rest position, and I start stretching it more and more and more and more. So at the beginning the force is 0, and then the force gets more and more and more and more and more and more like that, right? And I want to stretch it until a certain position. Let's just call it xf. So what I ask myself is, okay, well, now here the force is 0, here the force is, I don't know, f something, and here, and it goes through a number of values. So which one should I use here? Should I use 0? Should I use this one? We have a problem. This formula doesn't seem to tell us which force to use. The answer, of course, that we should use when we have this formula is the average. So not this one, but this one here. However, this will only work if this is linear. Now, another way to see this is, well, okay, this force is changing, but if I restrict myself to a very little change, then I can kind of assume that the force is constant, right? So I can say, okay, well, in here, let's just say that the force is 0, and then here is a little more, and here's a little more, and I can make these tiny little squares where I can multiply the force by a tiny displacement, and if I add them all up, then I will get the total work that I did. Just force times displacement. So that's this little area under each one of these rectangles. Of course, if I want to really get this formula without any kind of approximation, I need to make these rectangles infinitely small. But if I do that, what I'm going to get is exactly the area under this graph. And I'm in luck because I know how to calculate the area of a triangle. So how much work do I need to do to stretch this thing from 0 to a certain distance xf? Well, that's easy to calculate. It's just the area under here. So work will be equal to this force, that's the maximum force. Now, how much is the maximum force? Well, remember that force for a spring is kx. So in this case, the maximum force is kxf. Good. So work will be equal to kxf, and then multiplied by the base, which is just xf. So I'm going to just square this, and then, of course, the area of a triangle is height times base over 2. So I just need to multiply this by 1/2. And that's the work that I need to do in order to stretch a spring. But this is way more important than just finding the work of how to stretch a string. What I found out is that if I want to find the work that I need to do in order to counteract a certain force, or the work that a certain force does when that force is not constant but variable, all I need to do is find the area under the fx graph. So I make myself a force displacement graph, and I calculate the area under it, and then I get the work that the force does. Another thing that's interesting to calculate, and that will be very handy later on to defining potential energy, is the work that gravity does to a certain mass that's at a certain height, h. And in order to calculate this work, again, all we need to do is to use the equation work equals fs cosine of theta. Now, first we're going to imagine that this mass is just falling this way. Now, if this is falling this way, then the displacement goes in the same direction as the force of gravity. So theta is 0, and this is just 1. So just force times displacement. Now the displacement, of course, is just going to be h, which is how much it moves. And how much is the force going to be? Well, the force is going to be the weight, which is m times g, as you know. Therefore, the work done by gravity will just be work equals force, which is mg, times displacement, which is h, and times cosine of theta, which is 1. And we get that gravity will do a work equal to mgh on this thing. Good. Now, how about when this thing doesn't go straight down, but goes like this? What is the work that gravity is going to do? Well, let's find out. So I'm just going to draw this path, like this, and this can just be arbitrarily modified to make this as long as we want, or we could even make this diagonal. This would just mean that the steps are very small. Alright, so let's just do that. And now, in this part here, the work done by gravity, again, since this is parallel to this, is just going to be mg times this part here, and then this part here, and then this part here. And of course, if we add up all the vertical parts, we're going to get h. So the total work vertically is going to be mgh, as we calculated. How about the horizontal work? Well, in this case, this is horizontal, and therefore the angle between the displacement and the force is exactly 90 degrees. So this is 0. So the work that gravity does when this is horizontal is 0, which tells us that then the total work is still mgh because all the horizontal parts don't count. And since I can do this as small as I want, this is also the same thing, because I can always zoom in here and it will look something like this. I can turn it into a bunch of things that go down and a bunch of things that go to the sides. So what this tells me is that no matter how I move something in gravity, if it's like this, or straight down, the work that gravity does is always going to be mgh. And that is a remarkable result. I mean, don't you find it extremely interesting and bizarre even, that doesn't matter which path I take in gravity, all that the work depends on is the difference in heights. And it's this property that is going to allow us to define gravitational potential energy in a moment. Now we're in a position to start defining what we usually call potential energy. That should really be called something like position energy, because it's energy that's related to the position. Now, but first we need to define energy. What is it that we mean by energy? And energy is just the capacity to do work. So if I put this mass on top of here, and I let it go, it's going to accelerate, go to the ground, and if, for example, I put a mill here, so like a water mill, something like this, my mass is going to move it, and it's going to be able to do work. So this mass here, when it's over here, has the capacity to do work. Therefore, it has some energy. And this energy is related to the position that it occupies. So if I put the mill over here and I let this fall, this is going to move the mill, because this has the capacity to do work. And I gave it this capacity to do work by putting it up here. Now, we can define potential energy as basically the work that I need to do to place the system in this position. Now, for example, I have this mass here, and if I want it to be able to do work, I need to put it up there. And in order to do this, I need to do some work on the mass. And how much work do I need to do on the mass? Well, exactly the opposite of gravity. So I need to cancel gravity, so mg, for a height h. So the work that I need to do to lift this up is exactly mgh. And therefore, that's the potential energy that's going to be stored in this mass once it's here. Because we can see that once I release this, then gravity is going to do exactly this work on this mass to bring it down. So I do some work on the mass, it stores energy, and then it's the force of gravity that does the work for me. Therefore, this thing has the capacity to do work. How much work exactly? Well, mgh, because it's the work that gravity will do for me once I let this down. Now, there's something that's very important that you understand. So I will ask you this question. I want you to think about it for 10-20 seconds, pause the video, and let's see if your answer agrees with mine. And what I want to ask you is, where is the energy stored? So I lift this up here, and I'm telling you that this thing now has potential energy, but what has the energy? Does this have the energy? Does the Earth have the energy? Does the air have the energy? Where is the potential energy stored? Pause the video, think about it for a second. Now, I don't know what answer you came up with, but the actual answer is much more subtle than one could imagine. And the answer is that the energy is really stored in the system itself. The energy is not in the mass, and it's not in the Earth, it's in the mass-Earth system. In fact, it's stored in something called a field, the gravitational field, that we will talk about later on. You have to imagine that we're all stuck to the Earth by some kind of spring that is the gravitational force. So every time that I try to take this mass and put it up, I need to do some force, and I need to, overcome some resistance from the force of gravity. So that's where my potential energy is stored. This, some kind of invisible spring called a field, called in this case the gravitational field, that stores all this energy. And when I release it, this spring just goes back to its natural state, so that this thing goes back down. So the potential energy is not stored in the mass, it's not stored on the Earth, it's stored in the system, or if you want, in the field between both bodies. And this will be very, very important when we talk about atomic physics and when we talk about electricity, because with the Earth, you can just say, well, the potential energy is here and that's fine, and things work out. But once you have two charges, for example, it becomes very, very iffy to say that the potential energy is here or here. And actually, it's just stored in both of them. And to be more precise, it's stored in the field between them. Now, the same way that we define gravitational potential energy as the work that we need to do to put the system in that position, we can also do this for a spring, right? So here's our spring. And we said that if we wanted to move this spring a certain distance, xf, we had to do a work equal to 1/2 of kx squared. So we can use this to define the potential energy of a spring. A spring has potential energy. Once I move it from its equilibrium position by a distance x, there's an energy stored in there of 1/2 of kx squared. And I know this because once I release it, this thing is going to do a work equal to 1/2 of kx squared on whatever it is that I put here. So when I compressed it, I gave the spring the ability to do work. And in the case of the spring, it's really clear where the energy is stored. It's in the spring. In this case, we can see the spring. In the case of gravity, we cannot see the field, but it is just like a spring and it's there, even though we can't see that. Now, I told you that things that have the capacity to do work have energy. And they can have energy because of their position, but they can also have energy because of their movement. For example, something that's moving very, very fast, if I put, for example, a spring here, it's going to compress it. So therefore, it's going to do work on this spring, even though this doesn't have energy because of its position. The energy in this case is because it's moving. So you can have energy related to your position and related to your movement. The energy that's related to your movement, we call it kinetic energy. And we can actually calculate it. How? Well, just the same way as we did before. Before we said, well, if I want to calculate the potential energy, I need to find out how much work do I need to do in order to put the system in this state. Similarly, if I find how much work I need to do to make this move at a certain speed v, I will find the kinetic energy that this thing has if it starts from a speed of 0. Okay, so let's just say that the initial velocity of this guy is 0, and the final velocity of this guy, I'm just going to call it v. And what I want to know is how much work I need to do on this thing to get it to a final velocity of v. Now, in order to do this, all I need to do is use a little bit of kinematics, and that will be the last time I need to do the kinematics, because after then, I will just be able to use the fact that kinetic energy equals work, and that's it. So let's calculate the work. Well, in order to accelerate this, I need to move this certain distance d, which I don't know. So I'm just going to write this down. Work will be equal to F times d. Now, I also know that force equals mass times acceleration. So I'm going to substitute that in. Mass times acceleration times the distance. And now what I need to do is put this in terms of the velocity, both the acceleration and the distance. Now I know that the final velocity is v, and that the initial velocity is 0. And I know that acceleration is the increase in velocity over the time. But in this case, the increase in velocity is just v, because the initial velocity is 0. So then I got that acceleration is just v over the time that it takes me to do this. Similarly, I know that the distance is the average velocity times the time, and the average is the maximum, v, minus the minimum, plus the minimum, which is 0, over 2. So v plus 0, v over 2, v over 2. So equals v over 2 times t. And now all I need to do is plug this thing in here and plug this thing in here. So let's do that. I have that the work that I did is equal to m times v over t times v halves times t, and you can see that these two t's get cancelled out. V times v is v squared. So let me just show you this with a different color, and we get that the work that I did on this thing is 1/2 of m v squared. Therefore, this is the expression for the kinetic energy that this thing gained. The energy related to the movement of this thing is the work that I did on this thing in order to make it move at that speed. So we can rewrite this formula here. Let me zoom out and make it bigger. That the kinetic energy of a body is just 1/2 of its mass times its speed squared. And this again is going to be a very useful formula that we're going to use all the time. So it's very, very important that you're familiar with it. It's in your data booklet anyway. But what you need to do is understand what it means. Again, this is IB physics. Knowing formulas does not go anymore. You need to know what they mean, and you need to know how to get them. If you don't know how to deduce this formula, then you're going to be in trouble, especially if you're doing HL. Now we've seen both potential and kinetic energy, and now what we want to do is to put them together and finally state the law of conservation of energy. And remember that conservation means that something stays the same. And a little bit like in momentum, if we have a system and there's no external forces acting on it, actually if there's no frictional forces acting on it, we will find that energy, what we call mechanical energy, is conserved. And mechanical energy basically means either potential energy, which remember is energy based on the position of something, or kinetic energy, which is energy based on the movement of something. Now this is actually pretty easy to see. Imagine that I have a box that is at a certain height h, and I let it go. Now if I let it go, gravity is going to do a work on it equal to mgh. We found that out before. And we know that when I do work on something, all this work turns into kinetic energy. So this means that all the work that gravity did, which is mgh, will turn into kinetic energy, which means that this mgh has to be equal to 1/2 of mv squared at the end. So we see that the position energy at the beginning has to be equal to the kinetic energy at the end. this same kind of argument works if I have something that's already moving down, then mgh will be equal, mgh will be equal to the increase in kinetic energy, but I will still then have an equality that the sum of mgh plus the kinetic energy at the beginning will be equal to the kinetic energy at the end. And this works, of course, backwards when this thing is moving up and then it loses energy because gravity is doing work against it. So we can see that if we measure the potential energy and the kinetic energy of a body at the beginning, and then we measure it at the end, the sum of these two quantities has to stay the same. And this is extremely important to solve all kinds of problems in physics. As I told you in the last video, every time that you see a problem, the first thing that you need to ask yourselves is, can I use momentum conservation? And then you need to ask yourself, can I use energy conservation? And only if these two options fail you, then you go and try to ask something else. But any problem in the world will be way, way, way easier if you can turn it into a conservation of something problem. Now, this actually works, but only in absence of frictional forces. When there's friction, there's a problem. Some of this kinetic energy, so imagine that we have this potential energy, and in theory, all this work would go to kinetic energy, but in practice, some of this work is lost because there's another force that we're not seeing that's done by the air that's slowing this thing down. So what will happen is that by the time this thing reaches the end, this kinetic energy will be lower than the potential energy this thing had at the beginning, because some energy has been lost to its surroundings. Now, this doesn't mean that energy is not conserved. Energy is always conserved. What happened here is that energy degraded. We had mechanical energy that turned into thermal energy. That is, it turned into the random motion of the molecules around this thing. Basically, it heated up the air, and all this heating up of the air is energy that this box lost. Now, we can make this into an actual statement, into a very mathematical statement, and what we do is say this, that the decrease in the energy that we have is equal to the work that the friction forces do. So for example, imagine that I have a box that's sliding, and it has, let's say, 200 joules of energy. Now, imagine that there's a frictional force that acts on it. The frictional force is 20 newtons, and it acts on it for 10 meters. So I ask myself, how much energy did this box lose? And the answer is, well, first let me zoom out. The answer is that the decrease in energy will be equal to the work of the force of friction, which is, again, force times displacement, so 20 newtons times 10 meters, and times the cosine of 0, which is 1, that's equal to 200 joules, which means that the frictional force will actually eat up all the energy of this thing. And this means that after 10 meters, this box will stop. Similarly, we could have a different problem. We could say something like, I have a box that has 200 joules, and there's a frictional force of 20 newtons. How long is this going to go until it stops? And then what I would do is like, well, I know that it has to stop, so this has to be equal to the energy that it has, and then I would isolate to get the distance. Alright, so here's a picture of a cat, just because this video I know is really long, and I'm pretty sure you're a little tired. So look at this cat, relax for a while, isn't it cute? And now we can move on and keep working. Alright, let's go. Now, I apologize for this extremely long video. I know this is a lot, but you need to know it all in order to do the problems, because the problems are not in order, and basically they require you to know everything at once. So there's no easy way to do this. Now, we are going to talk about the relationship between kinetic energy and momentum. And remember that normally, when we have a momentum conservation kind of thing, we have a couple of balls that collide with each other, and then they go their separate ways, or sometimes they go together. But basically there's a collision, something happens, and then things go somewhere. Now, I told you that in these collisions, momentum is always conserved. Now, I would like you to pause the video for a moment and ask yourselves, is there if there's no external forces, is there any possible circumstance where momentum is not conserved? Yes or no? So pause the video. Okay, hopefully you did what I asked you, and the answer is no. If there's no external forces, momentum is always conserved, because remember that conservation of momentum is a consequence of Newton's third law, and Newton's third law always applies. It's not something that you can optionally do sometimes. It always applies. Every time there's an action, there's an equal and opposite reaction. Therefore, if there's no external forces, momentum is conserved, period. However, how about kinetic energy? Do you think that kinetic energy is always conserved in this kind of collisions? Yes or no? Pause the video, give me an answer in your head. Okay, hopefully you answered no. And the reason why the answer is no is that, for example, when these two things collide, there's a sound. And a sound is a wave that carries energy to your ears. Where did this energy come from? Well, obviously, from the two balls that were colliding. Therefore, the energy at the beginning cannot be the same as the energy at the end. Some energy has been lost to sound. Equally, some energy will be lost to vibration, friction, all kinds of stuff. Therefore, chances are that when two balls collide, kinetic energy is not conserved. However, in some cases, there's so little energy lost that we say that kinetic energy is also conserved. In this case, we call those collisions elastic. And elastic just means that kinetic energy is conserved. When kinetic energy is not conserved, we call these collisions inelastic. And all inelastic means is that kinetic energy is not conserved. Now there's a special case, which is when these two balls end up merged together, so they all go at the same speed v. In this case, we say that the collision has been perfectly inelastic, which means there's no separation between these two. They just stick together, move with speed v. So again, elastic, kinetic energy is conserved, or at least so very little is lost that we can just approximate it by being conserved. Inelastic, kinetic energy is not conserved. Perfectly inelastic, the two balls stick together. Now this is the very, very, very last thing we do, I promise. So bear with me, please. We're going to talk about power. This is really easy. All we need to do is think about work that we do per unit of time. So imagine that I have an elevator that has a very easy job. It has a mass, and its job is to take it up. There. Now, how much work does it have to do? Well, of course, mgh. So the work that my elevator does is mgh. However, I have two elevators in my company. One takes 3 hours to do this, and one takes 5 minutes. Which one would you rather buy? Now, of course, you would rather buy the one that takes 5 minutes, because it's not so much about how much work you do, but about how fast you do this work. But work does not give us this information, so we need an extra quantity, and we call this quantity power. And power is just how much work, or the increment of work, how much more work I did in a certain increment of time. So basically is how much work did I do and how long did it take me? So it takes me how much work I did every second. This is very important. So for example, if I have a car, I want it to have a lot of power because I want to accelerate from 0 to 100 in 10 seconds, not in 2 hours. If it takes me 2 hours to accelerate from 0 to 100, I'm going to be in serious trouble when I try to overtake somebody in the road. So anyway, this is the definition of power, and we use these a lot, for example, in electric circuits and when we're speaking about mechanical devices, engines, things like that, where we want to know how much work I can get done per unit time.